All right, Ozarka here. We are going to be going over complex numbers in this video. Namely, we're going to be going over those three objectives that are kind of listed right there. So identify and simplify complex numbers, add, subtract, multiply, divide complex numbers, and then simplifying powers of I. I'm going to assume that you've never heard about this I thing that I just wrote right there. It's to simplify powers of I. That's basically the imaginary number units. We're going to go over in more specifics on what a complex number is in this. So if you have no idea what I'm talking about yet with these objectives, we're going to go over them right now. All right, imaginary numbers. It says right here, we've been studying lots of equations, but not every equation involving real numbers is solvable with real numbers. And that's basically what a lot of mathematicians do. They're trying to solve a problem and, we can't solve this using the numbers that we've already created in our math minds. We're actually just going to create a new set of numbers, and that's essentially what we're going to be doing in here. The same kind of thing actually happened with negative numbers. So we had all these positive numbers, we had zero, and then someone thought of the idea, like, what about these negative numbers? And they didn't exist, before that, which kind of sounds silly now because now it's just part of, general knowledge that there's negative numbers. But back then they were completely new. People viewed them almost as imaginary because now it's like, how can you be in the negative? But if you redefine it as there's a number line and you can go to the left of zero, then you're redefining what numbers are, because now you can have those negative numbers. Imaginary numbers are the same kind of way, and it's based on the entire premise that you can't take the square root of a negative. Okay? So like this part right here, this I is actually defined as the square root of -1. And the reason you can't take the square root of a negative is because a square root, here I'm actually just going to kind of write down an example over here to have this make a little bit more sense. But say I was doing like the square root of 4. Well, the square root of 4 is, you're basically thinking about two numbers that are positive, in this case because it's a principal square root. But you're thinking of two numbers that are the exact same, then when multiplied together, you would get 4. That's basically what the square root of 4 is saying. It's saying what number, if you multiply it by itself, that's positive, would be equal to 4. And the answer for this is 2, because 2 times 2 equals 4. Okay, but the problem with, let's just say it was -4, for example, is there's no two numbers that are exactly the same. So you can't multiply two numbers that are exactly the same and get a negative value out of it. Okay? So for example, if you did 2 times 2, again, you get 4. At the same time, if you did -2 times -2, you would also get +4. So how can you multiply two things together and get a negative out of it? Okay, so I'm multiplying some number x times some other number x and somehow getting something that's like a negative value. And then, x squared. So negative of whatever the x squared is. And that's impossible based on real numbers. So we mathematicians invented this imaginary number unit where now you can actually solve that out with I, basically, because it's equal to the square root of -1. It is a fundamental, attribute of what a complex number it is, basically, with the imaginary part anyway. So the main thing that you have to understand on this is that I is equal to the square root of -1. We're going to go into more detail about how this is used to solve problems involving, numbers that have an imaginary number component to it. But for right now, just make sure you understand that I is equal to the square root of -1. And then it says right here, imaginary numbers can be written in the form of b times I, where b is a real number. So you don't always just have I, which in essence, I is 1I, but you can also have 2I, 3I, 1/2 I. You can have all these other values as well. And whatever those values are for I, that would be b. So you could have just regular old I, you can have 2I, 3I, -6I, and the b values would be just whatever is with it. So like if I was going to highlight what the b value is, this would be the b value for this case. With the 2I, it would be the 2. The -6 would be the b for this one. With the I, it would be 1. It's just invisible, but that's what the b value would be. So if you notice, it's a real number, positive or negative, or 0, you can actually have 0 as well, times I. Okay. An interesting thing about I is that when you square it, you get -1. So you square I and you get a -1. We just talked a second ago about if you multiply two numbers that are the same, you can't get a negative number. Unless, again, you use imaginary numbers. So now it's I times I, so that's two values that are exactly the same, and then you actually get a negative out of it. Okay, and it says no real number has this property. It's impossible, like I just said, using that blue line over there as kind of an example. And what you can do is you can actually factor out any negative. We're going to be doing this with a bunch of example problems in just a second, but you can factor out a bunch of negatives, the negatives in the square root by using that I. So if you notice right here that the main rule that I want you to see on this is there is a square root of a negative value in there. You can just pull the I out right there, and then the k becomes positive here. And in this case, we're just going to assume that k is a positive value for this purple problem. But it'll make more sense when we actually do more examples involving this little rule basically that we're going to be using for taking that square root, that negative outside of the square root by putting an I there. Okay, so that's basically an intro. A lot of this stuff with imaginary numbers that you kind of need to see it in action to make sense of it. So that's actually what we're going to do now. And it is really important to go back to what we talked about originally with complex numbers. By definition, what a complex number is, so I'm just going to kind of circle this and put this over here. A complex number is anything that can have this format where it's A, and A can be any real number, plus B is also any real number, times I. Okay, that's essentially the definition of what makes a complex number a complex number. If you can write it in this form, a plus bi, it's a complex number. A can be any real number, B can be any real number, and then you have that I component in there as well. And again, it is important to note that A and B can be any value, negative, positive, or even 0. Okay, so complex number has an imaginary component to it. It's actually really interesting to think about, but any number that you've seen ever has actually been a complex number. You just didn't realize it because you probably didn't know the definition of what a complex number is. Because even if there is, like, say b is equal to 0, you still have that a value, it's still considered a complex number. So even if there is no, if there's a 0 imaginary unit, that's completely fine. If b was equal to 0, it'd still be considered a complex number because it can be written in this format of the a plus bi. But enough of that. Let's actually do some examples. I think it'll kind of solidify the understanding of this concept a little more. All right, so this one right here, it says, write in terms of I and simplify. Okay, so you cannot have the square root of a negative in there anymore. It has to be in terms of I, and it has to be completely simplified. So we're also going to review the simplification rules of square roots. So this will be kind of fun. First thing that I'm going to do is what we talked about before is I'm actually going to take that negative and I'm going to make it positive and then pull the I in front. That is the main rule that I want you to see when doing these problems. You can't have the square root of a negative, so just take an I out of there and make it positive. So I'm actually going to rewrite this. That red is just kind of me showing my work, but I'm going to show my work a little bit more formally. So you have I times the square root of 40 like that. Okay, so right now it's written in terms of I, but that second part right here, it's not actually simplified. So we need to simplify that right now. All right, now in order to simplify this, there's a number of different ways that you might have seen before. Sometimes people use factor trees, and that's totally fine. I'm going to factor this just the same as it would be a factor tree, and just kind of show you, I don't know, I guess a more parsed out version of that. So the square root of 40 can actually be broken down into the square root of 4 times the square root of 10. Okay, and you could have broken up the 4 and the 10 a little bit more if you wanted. In fact, I'm actually going to do that just for the sake of the video. But if you wanted to, you can just simplify the square root of 4 right away to be 2. But just for fun, let's actually kind of parse this out a little bit more. So the square root of 4 is actually the square root of 2 times the square root of 2. So root 4 is equal to root 2 times root 2. And then root 10 is root 2 times root 5. Okay, so if you notice what I have right there, I have the 2 times 2 times 2 times 5. That is 40, which is what's under the square root. So right now, everything we have, it's looking good. Everything is completely correct here. But the main thing you need to understand or remember is that whenever you have like twins, you're multiplying a square root of something times itself, basically, it's always going to simplify. This is basically going to cancel out and just become a 2. So root 2 times root 2 is 2. Okay, root 3 times root 3 is 3. Root 4 times root 4 is 4. If it's a root times itself, like that square root of some number times the square root of that same number again, it's always going to cancel out the square root and you'll just have that actual value. Okay, so if you notice, that's the only numbers that actually pair up like that. Okay, the rest of it is root 2 and root 5. So those don't actually pair up. So I'm going to kind of underline these in purple. These right here don't pair up, so those are going to stay like this. So your final answer, I'm going to kind of write the final answer over here because I'm running out of room. It's going to be 2, because it's just a regular 2, times I. So there's the 2 here and then the I. And then the root 2 times root 5, those don't cancel or simplify in any way, so you're just going to write root 10 there and that is the final answer for this problem. Okay, it's written in terms of I, and it's completely simplified. 2I times root 10. Okay, the next one right here, we have the square root of negative 49 over the square root of negative 7. First thing I'm going to do on this is pull out the I, just like we did before. So we're going to have I root 49 divided by I root 7. Awesome. All right, now I over I cancels, so we're just going to cancel that like that. And the square root of 49 is 7 divided by root 7. Now, it is important to understand that all the same rules of I, all the same rules of numbers simplifying apply for I as well. So I over I is 1. Just like 3 over 3 is 1, 4 over 4 is 1. I over I cancels out, and it's just 1 over 1. I could have written that in here, 1 over 1. Completely legal to do that. And then the next thing I'm going to do is simplify this here. One of the ways that you've probably seen before for simplifying, when you have a square root on the bottom in the denominator like this, is to actually just multiply the top and the bottom by whatever that root is. Because if you multiply a root by a root, it cancels it out. So now you'll end up with 7 square root of 7 over, so we're just multiplying across here, so 7 times square root of 7. Then we're going to multiply right here, square root of 7 times square root of 7. That's just 7. Again, the square root of 2 times the square root of 2 is 2. The square root of 3 times the square root of 3 is 3. The square root of 7 times the square root of 7 is 7. And then we have another, 7 over 7 that we can actually simplify. 7 over 7 is 1. And you have your final answer of the square root of 7. Now, if you notice, there is no I in this, and that's completely okay because the I is canceled. It did say right in terms of I, but if the I does simplify, you will not have an I in there anymore, and the answer is right there as square root of 7. All right, this next one, right in terms of I and simplify. Okay, so this is going to be a little more interesting. First thing we're going to do is pull the I's out just like we did before. You can make them positive and pull the I's out, just like that. Okay, I'm going to factor everything again. First of all, I'm going to actually lump the i's together, so it's going to be I squared. And then we're going to have root 3. That doesn't factor because it's prime. And root 12 is going to be root 2 times root 2 times root 3, because 2 times 2 times 3 is 12. Okay, so everything from the red and the orange there is completely equal. There's nothing that's not equivalent in that statement. Those are both completely true still. Now what we can do is we can combine these. Root 2 times root 2 is 2. And then root 3 times root 3 is 3. So really we have I squared. Let me do this in a different color. So now we have I squared, we have 2, and we have 3. So we basically can multiply all those together. So now you're going to have 6I squared. But I squared, if you remember, is actually equal to negative 1. And the reason for that is I'm going to write this right here. I is equal to the square root of negative 1. If you square both sides, I'm going to square I squared, I'm going to square this here. The squared and square root are going to cancel, and you have I squared is equal to negative 1. So that means you can rewrite this right here to be 6 times negative 1, which the final answer is obviously going to be negative 6. So again, it says right in terms of I. There is no I because I squared is equal to negative 1, so you're not actually going to see an I in this problem, and not all of them are going to have I. It is important to understand that, but you still do have to simplify it, and then if you do, you get negative 6 for the answer. All right, the next one, it says complex numbers. Okay, I kind of already preloaded your brain with this a little bit, but it's awesome to, power of repetition, go over this stuff again. So that's what we're going to do right now. It says a complex number is an expression of the form a plus bi, where a and b are real numbers. Okay, again, a and b are just regular numbers that you've already known about before. Square roots, negatives, zeros, positives, whatever it is, that's what a and b are. And then you have that I component as well for the imaginary part. And then it says in the complex number a plus bi, A is called the real part and B is called the imaginary part. Really, it should say BI is called the imaginary part because the B itself is not the imaginary, but the BI is part of the imaginary part. You don't really need to know that so much, but just want to throw that out there. The A and BI terms cannot be combined because they are not like terms. One has an I and the other one does not have an I. Okay, so you cannot combine them. We're going to go over that in more detail with the problems that we're going to be doing in just a second. But you cannot combine I, terms, things that have an I in them with non-I terms. All right, and then the next one, that last sentence right there, it says, but every complex number can be simplified to a plus bi. We kind of talked about that a second ago. Just make sure you understand that. You are going to have to simplify things, and it has to look in standard form a plus bi. The I part has to come second. So, all right, let's actually look at examples to kind of solidify this, because it's one thing to just say it. We need to actually do it. All right, so this right here, we have a real number of 3 and a real number of 7. This square root of -9 is actually imaginary because of that square root of a negative. It automatically makes it imaginary because you cannot have the square root of a negative. What we're going to do is we're going to combine the real numbers. So 7 and 3 is 10. Awesome. And then we're going to do the same thing we were doing before. We're going to pull out the I and then make it a square root of +9 rather than a square root of -9. From here, we can simplify that square root of 9 to 3. So your final answer should be 10 plus 3i. And if you notice with this problem, there is a real part, that 10, and an imaginary part, that 3i. You cannot combine them. So you cannot say this is 13 because it's not 10 plus 3. If it was 10 plus 3, that's 10 real number plus 3 real number. You can combine real numbers. But here, you have a real number and an imaginary number. 3i is imaginary because it has the I in it. You cannot combine them. The final answer is going to be that 10 plus 3i. All right, the next one, write as a complex number in standard form. So again, it has to be that a plus bi format. All right, first thing we're going to do here is we're going to combine the real numbers. So it's 3 plus 4, that's just going to be 7. Then I'm going to combine the imaginary numbers. Now we can add these imaginary numbers up because they're like terms. They both have an I in them. Well, -2i plus +2i is 0i. So your final answer, you don't want to write 0i in there, is just going to be 7. All right, the next one. Standard rules apply for this. We're going to do distributive property, -3i times -2, -3i times 5i. So same rules as before. So you have -3i. I'm going to parse this out. I know some of you can just do this in your head, but I'm just going to write it out for fun. So I combine the first one here, -3i times -2, and then I'm going to combine the other ones here, so -3i times 5i, so plus -3i times 5i. You get something like that. This combines here with the -3 and -2 to be 6. The I has to carry over as well, so don't just forget about that I there. And then we're going to plus -3 times 5 is -15. And then I times I is I squared. Okay, I am showing a lot of work on this. You obviously do not have to do this. Some of you can just kind of look at these and be able to do them in your head. That's totally fine. But if you want, it doesn't hurt to kind of write it out a little bit more. Okay, I squared, if you remember, it's -1. We just went over that a second ago. So if you want to rewind the video, you can see that I squared is equal to -1. So now this is going to be 6i plus -15 times -1, because again, I squared is equal to -1. Positive here, so negative times negative is positive. And then you end up with 15 plus 6i as the final answer for that one. All right, onward we go to number 7 here. And now we're multiplying two complex numbers together, and I'm gonna see what happens here. I'm actually going to, I'm gonna grid this out, I think. I feel like that's kind of the way to go sometimes with these. So with the grid, I'm gonna do one of these where it's like 5 minus I. And then I'm gonna make a line here. And I'm gonna say 3 plus 3i. And basically with this grid, wherever they meet, that's what I'm gonna multiply. So it's just kind of an organized way of doing this. Some people use FOIL or distributive property or anything like that. A grid kind of does the same exact thing, and it just makes it a little bit neater to kind of understand. Let me clean this up a little bit first. All right, cool. All right, so first thing we're gonna do is multiply where they meet. So this one meets with this one here. We're gonna multiply. So it's 15. And it would have done the same thing if you just distributed, but this should be negative. That's embarrassing. All right, negative 15. All right, same thing over here, negative I times negative 3. So that's just gonna be positive 3I. Same thing down here in the bottom left corner. So it's gonna be 15I. And then bottom right corner, it's gonna be negative 3I squared. something like that. Okay, now what we're going to do is add all those up. So when you're multiplying, it's like you're finding the area almost. And when you find the area, you're going to basically adding all those up. So it's going to be negative 15 plus 3i plus 15i minus 3i squared. Okay, I'm going to combine like terms here, but first actually let's get rid of this and make that a -1 because I squared is equal to -1. This and this will become positive. So you're going to have negative 15 plus 3. Well, that's -12. So I'm going to do -12 plus 3i plus 15i is 18i. And you have -12 plus 18i for the answer for this. Okay, next problem. It says write I to the 5th as a complex number in standard form. Okay, I to the 5th, anytime you see an I, you're gonna want I to the first power. So if there's an I in the problem, it needs to be simplified completely. The only I you can ever have is I to the first, unless the I is just completely gone, and then you wouldn't have an I there at all. So what we're gonna do with solving problems like this is just kind of show you a little rule that you can do to simplify any powers of I. So you can simplify any numbers where I is the base and it's like set to some exponent. So essentially what we're gonna do is I'm gonna write a little table here. So this is gonna be kind of more of a note section. And then eventually we're gonna get to actually solving this problem. But let's just do some notes really quick. I'm gonna do that over here in this space. Okay, so what we're gonna have here is we're gonna have n. N is just gonna be a variable, and we're gonna have I to the n power. Okay, and in these numbers for n, I'm just going to plug in 0 for the first one. So act like it's 0. This one is gonna be I to the 0 power. Well, anything to the 0 power is just 1. So I to the 0 power is just gonna be 1. Okay, next, I'm going to do a 1. Well, I to the first power is just going to be I. Okay, that's not really controversial. All right, now I squared, we already know, we went over that. That's going to be equal to -1. Okay, next we're going to have I to the third. Well, I to the third is equal to I squared times I to the first. Well, we know what I squared is because it's -1, and we know what I is because it's just, or I to the first because it's just I. So the answer for this one is just going to be equal to -I. Okay, and again, we're just using exponent properties. This 3 is basically 2 plus 1 for the exponent properties. So you can always break it up, add the exponents. But you end up with -I. Okay, and then a very interesting thing happens when we put a 4 in here. Now we have I to the 4th. Well, I to the 4th is just I squared times I squared. Well, we know that's equal to -1 times -1. So I to the 4th is actually just equal to 1. So what ends up happening here is you end up repeating every 4, you get a 1. Okay? And it always goes in that order. It goes I to the 0 is 1, then I, then -1, then -I, then 1 again. And if you keep going, 5, 6, 7, 8, at 8, it's also going to be equal to 1. I to the 8th power is equal to 1. So we're actually going to use this fact that any 4th power based I is always going to be equal to 1. And we can solve that for any of these problems. And that's what we're actually going to do with this problem right here, this I to the 5th. What we can do is we can turn this into I to the 5th being equal to I to the 4th times I to the 1st. Now we want to do the 4 because we know anything with a 4 is equal to 1. Anything that's a multiple of 4, the power is 4, it's going to be equal to 1. So now it's just going to be 1 times I, which is equal to I. And we just simplified I to the 5th. And you can do this for any, where I is the base and it's raised to some exponent. You can do this for any of them. You can do I to the 342 if you really wanted. And it's the same kind of process as anything to the 4th power or anything that's a multiple of 4 is going to be equal to 1. So while we're here, let's actually do another one. Just because this one was kind of simple, I want to actually do one that's a little bit more complicated. So what if I did something like, let's see here, I to the 271st power. Well, first thing I'm going to do is think of the biggest multiple that I can think of for 271. Okay, that I can just kind of pull out of there. That's kind of easy to work with. I don't want to overthink it, obviously. So what I'm going to do is actually take out 200. So I'm going to have I to the 200 times I to the 71. Now the reason I took out 200 is because 200 is a multiple of 4. Okay, you could take 200 and divide it by 4 if you really wanted, you would get 50. So that I to the 200th power would actually be equal to 1. So now we have 1 times I to the 71st power. Now from here, the 71, you need to do the exact same thing. Think of a really big multiple of some number that you can add to that 71 without going over 71, obviously. So I'm going to do 40, just because I know it's definitely divisible by 4. And we're going to have I to the 31. By the way, you could choose any numbers you want, as long as they're divisible by 4, multiples of 4, and it will work like this. So I to the 40 is equal to 1, so now you have I to the 31st power. Okay, a good number that's divisible by 4 for that. Let's just say 20. 5 times 4 is 20. So we have 20 and I to the 11th. Okay, still not breaking that I down all the way, but we're getting there. Slowly but surely. I to the 20 is 1, so now we have I to the 11th. Let's just do I to the 8th times I to the 3rd. Okay, I to the 8th is 1, so you have I to the 3rd. Well, I to the 3rd is I squared times I. And I squared is negative 1, so you end up with negative I for this one. So you can actually simplify I to the 271st power all the way down to just saying negative I. Okay, that's basically simplifying powers of I. There's going to be more problems in your homework to practice that, but I just kind of want to show you a few of those so it makes more sense. But the key is multiples of 4, multiples of 4, multiples of 4. Make sure you understand that. All right, conjugates and dividing. A complex conjugate of the complex number a plus bi is the complex number a minus bi. Okay, so if a plus bi, if you change it to a subtraction, they're automatically complex conjugates of each other. Okay, notice that in forming the complex conjugate, we negate the imaginary part, but not the real part. So only that middle thing changes. It changes from a positive to a negative. Okay, those are conjugates of each other. An important property of conjugates. Okay, this is like, you might be thinking, why are we doing this? Well, this is why right here. If you multiply complex conjugates together, you end up with a real number. That's crazy. Okay, let's zoom in on that. If you multiply two complex numbers together that are conjugates of each other, you will always get a real number. They will always simplify out that way. And the reason for this is, I can kind of show you by distributing. If I multiplied this by a here, you would get a squared plus abi. Okay, and then we're going to do the same thing again, only this time we're going to distribute this to the negative bi. So it's going to be negative abi minus b squared I squared. Now from here, you'll notice these middle terms are just cancel out completely. So the things with i's in them completely cancel out. There's still something with an I squared though, but we know that I squared is equal to negative 1. So this I squared becomes negative 1. The negative right here becomes a positive. So negative 1 times that negative b squared is just positive b squared. And you end up with a squared plus b squared. You are going to want to remember this formula here, a squared plus b squared. Whenever you multiply complex conjugates like that, you are always going to get an a squared plus b squared. If you want, you could distribute like I did. But once you know this rule, it's better to just kind of use the rule to find the answer. So this is very abstract. Obviously, there's a's and b's and not real numbers all around like normal. So we're actually going to do some example problems to kind of solidify this a little bit more. So let's do that right here with this simplifying 3 minus 2i times 3 plus 2i. Again, these are complex conjugates of each other because it goes from minus to plus here. There's a minus and a plus. As long as those are opposites in the middle, they're complex conjugates. The shortcut for this is square the first number, square the b term. So the b is whatever's with the I there. And it doesn't matter if it's positive or negative, you're always going to just add the middle up here. And then it's going to be 9 plus 4, and you're going to get 13. And if you wanted to, you can literally go through this problem and solve it, out like the full way, distributive property, however you want to do it. I'm just kind of showing you the shortcut of what you can do if you really wanted to do it. Is just square that first one, square the b, and then just add those together. And again, it only works with conjugates. It doesn't work if they're not conjugates. You have to actually literally, work the whole problem out if they're not conjugates like that. This is a special trait for conjugates. Now, why are we doing this? Because you can't have an I in the denominator. For whatever reason, mathematicians made a rule that it's not fully simplified if you have an I in the denominator. Okay, so you're going to be looking at certain problems, for example, this one right here, where there's an I in the denominator. Same with the one in number 11, that we're going to have to simplify by getting rid of that I in the denominator. And the only way to get rid of an I is to multiply by that conjugate. That would get rid of that I in the denominator. And it's essentially what they do here with all this writing. I'm going to kind of ignore that for now just because it's not really super important for what we're going to be going over. What is going to be important is actually able to utilize what this is up here. So that's what we're going to do right now. So it says write as a complex number in standard form. So right now you should be looking at this problem and a light bulb should be going off in your head. Oh man, there is an I on the bottom in the denominator. We cannot have an I. So then we need to multiply by the complex conjugate. Now again, it's already a plus, so we're going to multiply by the minus. Now if you notice, I multiplied the top and the bottom by this because what I just wrote in red there, that's just equal to 1. 2 minus I over 2 minus I is equal to 1. So I didn't change the value of that original expression. I didn't change the value of this by multiplying it by some fancy 1. So that's why you had to multiply the top and the bottom. Make sure you do both each time you do that. We're going to distribute this top one to the 2 and then to the negative I. So you'll get 2 minus 8I minus I plus 4I squared. So that's the top part. Divided by, the bottom part is just a complex conjugate. So I'm going to square the first one, square that B term for the second one. So squared, squared, and then add them together. All right, from here, I'm going to simplify the numerator. This is going to be equal to negative 1. So that's just going to be negative 4. So it's going to be 2 minus 9I. So I can simplify this right here. Negative 8I minus I is 9I, negative 9I. And then 4 times negative 1 is negative 4. Divided by 4 plus 1 is 5. Okay, not fully simplified yet because we have this negative 4 here and this 2. We're going to add those together and get negative 2 minus 9I all over 5. And that is the final answer. If you notice, there is no longer an I in the denominator, and that's the whole point. All right, the last one, write as a complex number in standard form. If you notice, there is an I in the denominator there. You cannot have an I in the denominator for whatever reason, so we're going to get rid of it. Okay, first thing we're going to do is multiply. Now, in this case, that's just an I. So it's like 0 plus I, so you could just do 0 minus I if you really wanted. So I'm just going to make this negative I here and this negative I here. Okay, so from here, we're going to distribute on the top. You're going to have negative 5I minus 6I squared divided by negative I squared. Okay, I squared is negative 1, so at the top, you're going to have negative 5I minus 6 times negative 1, so it's just going to be plus 6, divided by negative I squared is negative negative 1, which is just 1. So if you notice, there's no longer an I in the denominator, which is awesome. I'm going to rewrite this in standard form, so it has to be the real part first and then the imaginary part second. So you should get 6 minus 5I as your final answer. So that's a video on complex numbers. You should be able to identify and simplify complex numbers. You should be able to do the arithmetic, the add, subtract, multiply, divide on complex numbers, as well as simplifying those powers of I, where I is the base and then it's raised to some exponent. If you have any questions about anything in this video, let me know.